So here's an example of a problem that you might be asked to solve having to do with electric field. Let's say that there are two charges, a positive charge at the origin and a negative charge some distance 2a to the right of the origin, negative 2q, so twice as much negative charge as positive charge. In terms of these distances a and the amounts of charge q, we're asked to find the amount of electric field at the origin, the amount of electric field at this location P1, and the amount of electric field at this location P2. And I guess we're asked to find the magnitude and direction of the electric field at P1 and P2, not just the magnitude. I want to emphasize there are not charges at these locations. These are locations in space where if we did bring a test charge there, that test charge would experience an electric force, but I'm not saying that there are charges there. There are charges at those locations. So what's the electric field there? Well, it's undefined. It's sort of infinite. It's at a separation of 0 from a charge, and so I guess if we were to take our electric field equation from a point charge, we would see that as r approaches 0, as we got closer and closer to that point charge itself, we would be approaching an infinite amount of electric field. Said differently, a second charge located exactly at the location of that first charge would experience an infinite electric force. So that's not really a very good question. But we can figure out the magnitude and direction of the electric field at point P1. Let's do that, and let's do it by thinking about an electric field diagram. Come on there, computer. If I consider that I'm at this location, when we're thinking about the direction of an electric field, we're always imagining a positive point charge at particular locations. So if I were to put a positive point charge there, well, it would experience a leftward electric force from that positive charge and a rightward electric force from that negative charge. So an electric field diagram is kind of like a free body diagram, except that there isn't actually a body at that location P1. There's just two contributions to the electric field, one contribution from each of the two charges. You can see that the whole amount of electric field is this leftward amount of electric field diminished by that rightward electric field. Well, wait, what if the right one's stronger? We haven't actually done the calculation yet. Well, if we say that the electric field is that left red minus that right blue, if the right blue is stronger, we will get a negative answer and know that the net electric field is to the right at that point P1. Let's see. So now I'm substituting, and I'm going to get the magnitude of that arrow and subtract the magnitude of that arrow. Let's see, the magnitude of the left arrow is kq over a. Where did this a come from? Ah, yes, a. Oop, oop, oop. Oh, my old one uploaded. I'll deal with that later. That a there is the distance between that location in space and that positive charge that is creating that contribution of electric field there. And now the magnitude of that rightward arrow is how much? K times 2q over the distance 2a squared. Keep in mind, what we're finding here is the magnitude of that rightward arrow. So we substitute positive 2q there. Really, the rule is the magnitude of an electric field from a point charge is k times the magnitude of a charge divided by r squared. And the magnitude of this charge creating this rightward contribution to electric field, the magnitude is 2q. In other words, when I'm subtracting left minus right, when I'm subtracting left minus right, I'm subtracting a positive number minus a positive number. There's a temptation to want to put a negative 2q there because it is a negative charge. But if I did that, then I'd be taking a positive number minus, well, a negative number. That's not what we want to be doing. We want to be taking that leftward magnitude minus that rightward magnitude. This positive number minus that positive number. So positive 2q there. And the answer is that. Well, now let's work on getting the magnitude and direction of electric field created by those two charges at this location in space, point P2. Well, as you can see from the diagram in the previous page, the positive charge creates a straight upward contribution to the electric field. I imagine a positive test charge there. A positive test charge would experience an upward electric force from the red positive charge, and it would experience a positive charge at point P2 would experience an electric force towards this minus 2q charge. So the minus 2q charge creates a down and to the right electric field contribution. So what's the net horizontal component of electric field? Well, it's just the electric field from the minus 2q charge's x component. So let's find the whole magnitude of electric field contribution from the minus 2q charge, the whole blue magnitude, and then we'll find its horizontal component. I'm making a separate diagram here to keep track of the geometry. Okay, so here the actual distance, the d, is a root 5, because there's the distance a and there's the distance 2a. Okay, a root 5. And now the horizontal component of this blue vector is equal to the whole magnitude of the blue vector times, let's see, if this is the way that I have defined theta, then, is it really sine theta? Why is it sine theta? One wonders. I guess because if I imagine this triangle, yeah, okay, there it is. Yeah, sine theta, because like theta is tucked up there, and I'm imagining sort of this horizontal component, which is opposite the angle theta. Draw it bigger. Here's a corollary. If you have trouble keeping track of sine and cosine, draw it bigger. So the horizontal component of that blue vector is equal to the whole magnitude of the blue vector times the sine of theta. And what is the sine of theta? Well, the sine of theta is opposite to a over hypotenuse, a root 5. So I can make that substitution there. The a's cancel. And so, let's see. The x component is equal to the whole blue magnitude times 2 root 5 over 5, and the whole magnitude of that blue vector is what we get from the expression from electric field from a point charge, k times the magnitude of this charge, 2q, divided by the distance squared, the distance between the charge creating the electric field and the location in question. And simplify, simplify, simplify. Now, let's get the y component of the net electric field there. It's equal to that up minus that down. This down, this vertical component of that blue vector. It may be that that blue vertical component is bigger. If it is, math will tell us a negative result. And so we can get this net vertical component of electric field is that red magnitude diminished by that vertical component, which is the blue magnitude times the cosine of theta. The way I've drawn theta there. Cosine of theta from the geometry is a divided by a root 5. Substitute the magnitude of this red electric field vector contribution is kq over a squared. The rest is substitution, blah, 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 blah. And you've got it. So the net electric field is this quantity times this amount in the horizontal direction and this amount in the vertical direction. So I think we were right that the net vertical component is upward.